All right, let's dive into a really clever breakthrough in AI called linear attention. This is a huge deal. It's basically the secret sauce that lets AI models process massive amounts of information way faster than before. We're going to break down exactly how it works.
But first, let's start with a question you might have wondered about. Why can't a super powerful AI just read a whole book in one single go? Why does it always seem to need to break things down into smaller pieces? Well, the answer comes down to a fundamental roadblock, kind of like a massive computational traffic jam. And that traffic jam has a name: the quadratic bottleneck. This is the core problem we're talking about today. You can pretty much think of it as the villain of our story, and it all boils down to how standard AI models pay attention. See, for an AI to understand the context of a sentence, the standard way, what we call standard attention, forces every single word or token to compare itself with every single other token in that sequence. The first word looks at all the others, the second word looks at all the others, and on it goes. It's incredibly thorough, but as you can imagine, it gets really expensive. The computational cost for this process is what's known as O of n squared, or quadratic complexity. Now, what does that mean in plain English? It means if you double the length of the text, the number of calculations doesn't just double, it quadruples. If you triple the length, the work skyrockets ninefold. This cost just explodes, making it practically impossible to process something really long, like an entire book.
So how do we get around this massive problem? Well, this is where the big breakthrough comes in, a kind of elegant what-if moment in AI research that completely changes the game. It's called the kernel trick.
The part of the calculation that's causing all the trouble is a function called softmax. It's the part that helps the model decide which words are most important. The big idea with linear attention is deceptively simple. What if we just replace it? What if we could swap out that expensive part for a much cheaper approximation that gets us a result that's good enough?
And that's where this thing called a kernel feature map comes in. Now, don't worry about the Greek letter or the fancy terms. All you need to know is that this is our mathematical shortcut. It's just a clever function that gets us a very similar result to that super expensive calculation, but in a much more efficient way.
And this is where the real magic happens. By using that kernel trick, we unlock something called the associative advantage. This is the mathematical sleight of hand that gives us that incredible speed boost we're after. So let's walk through this little mathematical shuffle. We start with the original clunky attention equation. Then we swap out the expensive softmax part for our new efficient kernel function. And finally, and this is the genius move, we just rearrange the parentheses. That's it. We just change the order of operations.
And that simple change in parentheses is the entire trick. We go from calculating QK transpose V to QK transpose V. You don't need to be a math whiz to get the insight here. The letters Q, K, and V just represent how the AI asks questions and finds information. By simply changing the order in which they're multiplied, we turn an impossibly slow calculation into a lightning-fast one.
The researchers behind this put it perfectly. The deep insight is that attention becomes an associative computation. We haven't actually changed the ingredients, just the order we mix them. And that, it turns out, makes all the difference in the world. So here's the payoff. Just look at this. With standard attention, the cost grows quadratically, shooting up into the stratosphere. But with linear attention, the cost grows, well, linearly. You double the text, you double the cost. It is a total game changer.
And there it is. We've achieved O of n complexity. We've gone from quadratic to linear. The bottleneck is officially solved.
So this new method is way faster, way more efficient. It must be perfect, right? Well, not exactly. You know, like any great piece of engineering, there are always trade-offs. So let's talk about speed versus precision. The upsides are huge. You get that linear speed, you can handle incredibly long sequences of text, and it's fantastic for things like streaming data. The downside? Well, it's an approximation. It's not exactly the same as the original, which means it can be a little less precise and sometimes a bit trickier to train.
So why does this all matter to you? Well, think about the possibilities. We're talking about processing entire books or massive legal documents in one shot. Imagine real-time systems that can analyze a constant stream of information without falling behind, or even process every single frame of a high-res video. Stuff that was basically impossible before is now totally on the table.
So, to wrap this all up, I want to leave you with a simple but really powerful way to think about what's changed. This is the new memory model for AI attention. Here's the core difference in strategy. Standard attention's approach is to compare with everyone. Every word has to check in with every other word, every single time. It's exhausting. Linear attention strategy is completely different. It just maintains a running summary. As each new word comes in, it just updates a small, compressed memory of everything it's seen so far.
So really, we've just shifted from a full brute force comparison to a much smarter, compressed memory. It's a fundamentally more efficient way for an AI to remember and process information over time.
This breakthrough really does open up a whole new frontier for what AI can do. Now that we've broken the quadratic bottleneck, models can handle vast amounts of data at a reasonable speed. So, I'll leave you with this to think about. What previously impossible problems will AI solve next?